So we have seen the derivation of the binomial formula and some numerical example for how it can be applied to price options. Now let's look at different issues of um, applying the formula in different setup. So first we consider the continuous compounding. And we assume the continuously compounding interest rate is this lowercase r, and the dividend yield is delta as before. The period length is h. Now, the hedged portfolio parameters become delta is this e to the negative delta times h, and then the rest will be the same. Okay, and this borrowed money amount is also discounted using the interest rate R for the time period H. We have said before, if you think about the underlying, right, the underlying actually grows at the dividend yield delta. Okay, and what we are assuming here is that the underlying actually gave you the delta dividend, and you reinvest in the same stock. Okay, so if you put this negative power into the denominator, it will become a positive power. It's basically saying the spot price at time zero will grow at delta. Now in the borrowed money part, right, you have this discount at the interest rate, which is basically equivalent to 1 over R. That's the risk-free discounting we had before. Now put this delta and the borrowed money into our pricing formula. Right? What do we have? Again, something very similar to what we had before. The first term is the risk-free discounting, and then the payoff for the up and down states, option payoffs, is still there. We know that from the different stock price in the two different states. The denominator in the risk neutral probability are still the same. This the distance between the up and down proportions. The numerator, right? The numerator still something minus the downstate proportion, and then upstate proportion minus something. What is this something? It's we know the risk-free rate, right? Compounding should be there, and then we actually need to deduct the dividend yield. You need to deduct the dividend yield from it. Obviously, because you have this option, right? You don't have the underlying, you don't have the dividend accrued to you. So the dividend is deduced from the risk-free rate. And the length of the period is h. That's the continuous compounding binomial formula. Okay, that's how to incorporate the continuous compounding rate, the interest rate, and dividend yield into the formula. All right. Now we need to consider the construction of the binomial tree with continuous compounding. Now let me talk about the goal here, and I will draw a picture for that. So what we are trying to do is to consider not just one period or two periods, maybe several periods. Let me start to see, right? This is at the end of period 1, and then at the end of period 2, at the end of period 3, at the end of period 4. Okay? And we can keep doing it, but let's start to see what we can have. And we get this one. So from time 0, it can go up and down. And then from time 1 to time 2, you can go up and down again, and we assume that after 1 down up or up down, it go back to the same point here. Okay, so this is what we have seen for 2 periods, and I can keep doing it. This is for 3 periods at T3, what we can have. And now we have how many nodes? 1, 2, 3, 4. 4 nodes. Right? 1, 2, 3, 4. 4 nodes. And make it into the fourth period for the T4. T equals 4. Right? We can keep doing this, going up or down, up or down. So now 1, 2, 3, 4, 5. We have 5 nodes. And you can imagine I can keep going forward, right? Up, down, up, down. So this is so-called a lattice. What we can do is basically say for 1 day, right? You can chop it into 2 half days, and then even further, right, into finer and finer, shorter and shorter time periods. Then you have more and more time periods, and for each of those time periods, the stock price can go up or down by a certain proportion. And then what we can achieve is actually something like this. You can see certain price paths, right? Maybe like that. Maybe it went down and up, down, down, keep going down. Or it go change our color, going up, 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 down, down, up. Okay, you can start to have different paths for the stock price, or different trajectories for the stock price, and that allow the binomial model become closer and closer to reality. To get there, then what we have to know is basically for each period, how much it will go up or down, right? The up proportion or down proportion in each period. And ideally, we will make them the same for every period. Then we have this so-called recombining lattice, right? And it can go back to the same value, right? Let's say from this point, the yellow point here, go up, what happened? Go and down, and then if it went down and go up again, and went up and go down again, it will go to the same price. Okay, so that's a recombining lattice. And if we have this kind of binomial tree, then with finer and finer grades, right? You have shorter and shorter time periods. Potentially, we can price the options more accurately. So let's look at first how to get the up and downs. So we assume the up and down both have a first term that goes with the risk-free rate minus the dividend yield. Okay, the first term both go like that, and then it has a volatility portion. So sigma here is the standard deviation of the stock returns. We need to estimate it, and then this sigma will be adjusted using the H, the time period length. Okay, and with this kind of formulation, we do have the up and down up. Okay, you put them together, we will get this. Kind of go back. Okay, so it's the recombining tree or lattice. The two volatility terms go away. It's just two-period compounding. Just go forward for 2 periods, compounding at the risk-free rate minus the dividend yield. Okay, now let's think about the continuously compounded return and how can we get the sigma, the volatility standard deviation, right? So the return for continuous compounding returns, we take the log of the price change for time period H. And then the new underlying price at t plus h can be expressed as the spot price at time t compounded at this continuous compounded return. If we have more periods, you have n of periods with length h, right? And that will be a sequence of these continuous returns put together, and in the power, right, when you times each of these continuously compounded return for each period, time them together, then in the power, it's actually a summation of all the continuous compounded return. Okay, so let's assume that for each month, the continuously compounded return is R monthly I. Okay, and then the annual return will be the summation of the 12 months monthly return. Okay, 12 monthly returns. It's just go back to here. In the power, all these powers actually sum up. Okay, then we can think about the variance of the annual return, and this is summation. We take the variance of the summation of the 12 monthly returns, and if we assume there's no serial correlation, in other words, each of these monthly returns have no relationship with one another, independent of one another, you just simply sum up the individual variances. There's no cross term. The cross terms are zero, right? The covariances are zero. Once you sum that up, make another assumption saying each month the volatility are the same, right? For every month, the variance is the same. If they are the same number, then the annual variance will be 12 times the monthly variance. So the second equality assumes no serial correlation. The third equality assumes so-called homoscedasticity, meaning that every monthly return is the same number. Okay. So if this is the relationship, right, the annual variance equals 12 times the monthly variance. If that is the relationship, take the square root on both sides. So square root of 12 times the monthly standard deviation of the asset return equals to the standard deviation of the annual return. Okay, and then finally we can see that the monthly standard deviation can be calculated using the annual standard deviation divided by the square root of 12. Obviously, we are going to take the positive root. Let's think about this one whole period as 1. Then we can divide this one period into n equal portions, each with length of h. So the length is a smaller number here. It's equal to 1 over n. N is the big number. Okay. So n is actually the 12 here, and h is actually 1 over 12. So if we know the standard deviation over the longer period, then the standard deviation in the short period h is what? It's actually, I have said, if you have h equal to 1 over 12, right? The standard deviation sigma h for the short period h is the longer period sigma, right, over the square root of n, or say sigma times the square root of h. Again, h itself is 1 over 12, so square root of h is 1 over the square root of h. Okay. Also, this can work backwards. If you know the short period standard deviation sigma h, then the whole period standard deviation is sigma h divided by square root of h. Again, the square root of h is 1 over the square root of 12, so it's actually sigma h, the shorter period standard deviation, times square root of 12. Okay, it's actually the big number here, the square root 12 here. Okay, so what it says, again, this formula in the bottom is actually exactly where we started, the square root of 12 times the short period standard deviation, sigma h, here is the monthly, equal to your annual standard deviation, longer period standard deviation. So let's go back to see our assumption. Assume no serial correlation and homoscedasticity. We have this standard deviation as long as you know the standard deviation for some period, and then you can back out for either longer or shorter time periods. Now, remember in forward pricing, right? If for a stock, the forward price is the spot price times compounded at the risk-free rate and discounted at the dividend yield for the time period. Okay, this is our standard forward price calculation. So there's no uncertainty there. And then we need to add back uncertainty with this standard deviation in the return. Okay, kind of go up and down by 1 standard deviation for each period h, and this standard deviation will be adjusted with the length of h. So what we have assumed is basically both the up and down proportion have this fixed term, right? Fixed drift, kind of in risk-free rate minus the dividend yield, this fixed drift, and then this kind of volatility term, right, going up by 1 standard deviation or going down by 1 standard deviation. And that's the original assumption we have seen before. Okay, but this formulation, we actually have this relationship. Okay, this relationship, and let me know, right, in the up state after h time period, or you will get a up state price in the underlying, and in the down state there's a down state underlying price. The major difference is this volatility in the return, either go up or down. Okay, now we have the formula. We will have to estimate the volatility. So in finance, volatility estimation is a very important pricing business. Okay, if you have the volatility right, the option price will be correct. Obviously, if you have the volatility estimated wrong, then there will be some arbitrage opportunities for someone. Okay. Volatility computed from historical stock returns is so-called historical volatility. We can use weekly returns to calculate a weekly standard deviation, and then the annual standard deviation of the return will be the weekly standard deviation times the square root of 52. For standard options, we are talking about not exercised before expiration. If you remember, there are several cases of that. The volatility that matters excludes dividend because you won't receive dividend. So we use the ex-dividend prices in our calculation. And let's look my Excel. Look at my Excel calculation here. Okay, so where I started is using the daily closing value of the S&P 500 indices. And I calculated the daily return. Okay, with the daily return, I can calculate its standard deviation. This is the daily standard deviation. For weekly, I take the square root of 5, right, times the daily standard deviation. So from 79, almost 80 basis points for daily standard deviation, we have 1.77% for weekly standard deviation. For monthly, I assume 30 days in a month, and then there's 7 days in a week. So there's the week, number of week in the month times 5 days a week. Okay, so the monthly standard deviation can be 3.68%. Then annualize that, take the square root of 250 business days, okay, based on daily standard deviation. We have the annual standard deviation is 12.57%. So that's from daily standard deviation. What I'm doing here is I want to know how wrong my assumptions are. No zero correlation and homoscedasticity. It turns out it's not that bad. These assumptions are not that bad. The weekly standard deviation calculated for the same period from the weekly returns, okay, is 1.68. It's not very much different from 1.78. Okay, it's basically 10 basis point difference. Then the monthly standard deviation based on weekly returns is 3.48%. The daily standard deviation implied monthly standard deviation is 3.68. Again, this is quite close, 20 basis point difference for monthly. The annual standard deviation based on weekly returns is 12.14. Okay, the daily standard deviation derived annual standard deviation is 12.57. Yes, the difference is bigger, but as a proportion of the 12% something itself, the difference is not very big. All right. Now just look at a monthly. I use the monthly returns. Okay, only look at the monthly returns. Look at its standard deviation. It's based on monthly returns, 3.91. Still not very far from the 3.48 or 3.68. Okay, and annual standard deviation based on the monthly, right? I take the square root of 12 times the monthly standard deviation, get my annual standard deviation, 13.54. Again, not really very far from 12.14. The space for error, at least based on historical data, is not that big. And this is how you can convert from different time intervals, right? Daily, monthly, or if you would like, by seconds, milliseconds, calculate the standard deviation, and then you can extend that. Okay, this is the textbook calculation based on S&P 500, the index, and IBM stock itself. And you can have the standard deviation for several days. From different weeks, and then we get the kind of weekly standard deviation of either the S&P 500 index or the IBM stock price. And we can extend the weekly standard deviation to an annual standard deviation by time it to square root of 52. Okay, the number of weeks in a year. That's basically the same business I did in the Excel model. So as we have said, right, our goal is actually to get this kind of lattice, and because it can give us a lot of different scenarios going up and down, going zigzagging, and to achieve that, we need the grid of time periods become finer and finer. So for, let's say, for 1 month, right, you make into every hour, right? Each time period you're considering going up and down become every hour. And so what we need to do is basically divide one period into many more sub-periods with, well, equal length. And what we'll see is actually the up and down will get closer to 1. Basically, in the shorter time period, the range that it can go up and down becomes smaller and smaller, which is quite understandable. So the period length is still h equals 1 over n. This length will decrease as the number of periods you are going to chop this whole period into increase. We can do a numerical example. Let's say the risk-free rate is 8%, the dividend yield is 0, and the standard deviation is 30%. That's for the whole period. Okay. And for 2 periods, h will be a half. For 3 periods, h will be a third. Right? Here, if you think about for 2 periods, the up proportion is 1.287. Right? It's the 30% standard deviation times the square root of a half. The down proportion is 0.842. So that's for two subperiods. For 3 subperiods, the up proportion become 1.221, and the down proportion become 0.864. Okay, so the up proportion actually decreases a little bit, down proportion actually increases a little bit, both of them moving towards 1. Obviously, if you chop the whole period into finer and finer grades, right, your lattice become denser and denser. Right? Then let me show you what I mean by that. Okay, let's just say you have many okay, t equals 0. Right? Let's go up and down, and then go up again, go down again. go up and down, and here go down, up. Okay, you can make the lattice just become denser and denser with finer and finer periods to go. So then so same even for the same standard deviation, right? Each up and down proportion will change. The risk neutral probability will change accordingly. The option price will change, and hopefully, as we make our lattice finer and finer, the option price will become more and more accurate. Here I have my Excel model to take a look at the effect of increasing subperiods. Okay, 1, 2, 3, 4, 5, 6. So let's take period 4 here. If I chop my whole period into 4 subperiods, then the up proportion, right? What happened is this risk-free rate minus the zero dividend yield go at the D7 here, length of the periods. Okay, this grow at the length of the period, and then it's the same standard deviation, the brown number 30% times the square root of the length of the period. Okay, again, this is a smaller number. That the as more and more subperiods into the one whole period, the length of the subperiod becomes smaller and smaller. So the magnitude of going up and down becomes smaller and smaller. Okay, so this is from 1 to 6. The length of the time period becomes shorter and shorter, and you can see the up proportion become smaller and smaller going towards 1, and the down proportion going bigger and bigger, again, also towards 1. Okay, so if I consider the whole period, okay, just consider the whole period, let the underlying stock move once, starting from $41, okay, it'll go $59.95 or go down to $32.90. But if I have three sub periods, let it go one period. The range is smaller. The up state is only 50.07. The down state is 35.41. It's, the down state price is higher than 32.90, and the up state is much smaller by almost $10. Okay, so that just says, right, in the shorter time period, the stock move by less magnitude. That's what you have with a denser and denser lattice. Now let's think about how can we use the binomial formula to price American options. The whole theory doesn't change. The only thing we need to consider is actually the value of American option, or say the payoff of American option at different nodes. So what we have to consider is the option's value if it's left alive, not being exercised, right? So you hold it for another period and keep it alive. Then that's one value. Another possible value is to exercise it on that node. Okay, you get an instantaneous payoff, or say the intrinsic value out of it. Right? For call, it's either 0 or the stock price minus the strike. For put, it's either 0 or strike minus the stock price, right? Whichever is higher. Now, using put option as an example, what we need to think about is the value of this put at a node. Right? It's the maximum between exercise it, right, or keep it for another period. Now this node is somewhere in between, right? Somewhere between the ending node and the first node. So either you got the exercise value, right? Obviously, if you exercise it, it should give you some positive value or 0. But 0 is obviously dominated by the value that keep it alive. So as long as there's some value to consider now to exercise it, right? It still has some time value in it. 0 is out. We don't need to consider 0. And then what is this alive value, right? It's exactly the value implied by our binomial formula for the next period. It goes from current value and think about one period later. So t plus h, you have this put value in up state and put payoff in the down state for after h, time period h. This up state times p star, the risk neutral probability for up state, and the y minus p star risk neutral probability for the down state. Okay, discount this sum using the risk-free rate. So this is exactly a binomial formula to calculate the put options value if it is kept alive. Okay. So using the risk neutral probability and the binomial formula, we calculate its value to hold it for another period, for another h. Yeah, or you exercise it now to get k minus s, whichever is bigger, right? And that will be the payoff, or say the value of that put option on this node. So for American options, what we do is at each node, we check for early exercise. Okay, if the value of the option is greater when exercised, we assign the exercise value to that node. Otherwise, we assign the value of the option unexercised, the value implied by the binomial formula. And as long as we have the ending node values or ending node payoffs, right, we can work back through the tree. Okay, just like what we have done before, backward induction. Now let's talk about several issues that we need to notice or we need to know when we apply this binomial formula on other assets. So our binomial model developed thus far can be modified easily to price options on underlying assets other than stocks. But for different underlying assets, the construction of the binomial tree and the risk neutral probability will be different. Okay, you have to consider the asset's characteristics and so as to construct the binomial tree and the risk neutral probabilities. So we will look at stock indexes, currencies, future contracts, commodities, and bonds. There are at least 2 points we need to know for the CFA curriculum. All right. It's actually quite straightforward for a stock index. The previous formula for a single stock applies for pricing an option on a stock index. There's no question about that. All right, options on currencies. If you think about the forward exchange rate, right, it's the spot exchange rate. It's a direct code compounded at the difference between the domestic rate and the foreign risk-free rate. The R capital F here is the foreign risk-free rate on the foreign currency. Obviously, the time period length is H here. And then the exchange rate movement is still this, similar to our stock, right? We have for the stock, the minus term here is the dividend yield, but here it's the foreign currency interest rate. Okay, that's the asset you don't have. So deduct that, and going up or down by standard deviation in the exchange rate movement. So the risk neutral probability of an up move, right? Once you have the up move, you will have the down move, is this continuous compounded rate at the difference between the domestic risk-free rate and the foreign risk-free rate for time period H, right? Minus the down proportion divided by the difference between the up and down proportions. So that's for currencies. Okay, we basically replaced the dividend yield with the risk-free rate on foreign currency. Now think about options on futures contracts, right? And again, for most part in this course, we will assume the forward price is the same as the future prices. The only up and down move matters because the price attached to the futures contract is already a forward price. Okay, the forward price movement is going up by one standard deviation or going down, and continuous compounding by one standard deviation. This is the up proportion and the down proportion. And then we need to consider this replicating portfolio, how much it worth. It must satisfy since the initial value of the futures contract is 0, and its value is the change in the forward price. So we have these two equations that has to be satisfied. Okay, except f here itself is 0, just up and down, and then what we have is you still have this delta. Delta is the difference between the call payoff divided by the change in the price, the change in the futures price, or the forward price. Okay, and then this borrowed money position turns out to be exactly the call premium. Okay, why is that? Because the futures contract requires no investment to start. Now look at this again, the expression for the borrowed money, right? This is exactly the upstate risk neutral probability given in here times the upstate call payoff plus the downstate call payoff times the downstate risk neutral probability, and then discounted at the risk-free rate. This certainly is the binomial pricing formula, so we have the call premium equal to the money that is borrowed. Now think about the replicating portfolio. Before, what we have will be a long position in the underlying plus the money that is borrowed. But now, since the futures contract costs nothing, right? The long position itself costs nothing. So in that replicating portfolio, the only thing you have is the amount of money that is borrowed, and it has to be the value of the call option itself. Okay, that's because the cost of the replicating portfolio is the call premium, and now all the value in the replicating portfolio simply all come from the borrowed position, the borrowed cash. So it is the call premium. Now this slide is an important point in the CFA curriculum. The idea is that sometimes it can be optimal to early exercise an option on a futures contract. And the attractiveness of early exercise comes from the fact is that once you exercise it, you get this futures contract and it's in the money, then you actually can earn interest on the mark-to-market proceeds. Okay, so think about the exercise of a call option on a futures contract. Right? You exercise it, the option holder pays nothing because it's the right to enter into a futures contract. But because it's in the money, you actually get the mark-to-market proceeds of the difference between the strike price and the spot, and the, let's just say, the current futures price. Okay, it's not the spot price. It's the current future price, the difference between the strike price specified in the call option and the current future price. Right? You see that is in the money. You exercise your call option, pays nothing because the futures contract itself costs nothing, but you get the proceeds of that difference between the current futures price and the strike price, and that can earn interest income. That is a particular case for futures. It's not the case for forwards. But what we need to remember is that sometimes it's good to early exercise an option on futures contract to start to earn interest income. Okay, now think about options on commodities. If there is a market for lending and borrowing the commodity, then pricing such an option is straightforward. But in practice, transactions in physical commodities often have greater transaction costs than for financial assets, and short selling a commodity may not be possible. So, from the perspective of someone synthetically creating the option, the commodity is like a stock index. If you borrow it and short sell it, there will be a leasing rate paid to the underlying. So it's equivalent to the dividend yield on the stock. Okay. So if you can borrow and sell the commodity, then you can apply the binomial formula, and the leasing rate on that commodity will be in the place of the dividend yield. But short selling can be a constraint. So pricing that option may not be that straightforward. Okay, let's think about options on bonds. And again, this is some important knowledge in the CFA curriculum. And it's basically saying one conclusion: you cannot apply the binomial formula straightforwardly to price the options on bonds. The only easy part is to say bonds are like stock that pay discrete dividend. Bonds pays coupons. Okay, that's the similarity between bond and stock. But bonds differs from other assets in two respects. First, the volatility of a bond decreases over time as the bond approaches maturity. We know from fixed income, the bond price basically moved towards 1. That's why the volatility of bond price decreases over time. So you have changing volatility. Remember, we constructed the binomial lattice using the volatility, but now the volatility is changing. So that's one difficulty. The second difficulty is the assumption that the interest rates are the same for all maturities and do not change over time, are logically inconsistent for pricing options on bonds. Okay, so let's go back to the binomial formula in pricing options on stocks, right? We assume one single risk-free rate for the whole period, and it doesn't change over time, right? I do not apply a different rate in early periods and kind of another rate in later periods. It's the same rate for the whole period. But for bonds, we know what the arbitrage-free pricing of bond depends on the so-called treasury spot rate, and for different maturity, you'll have different interest rate, right? Or say for different maturity, you'll have different yield to maturity. If you think about a single number, and then for all the different cash flows embedded in the bond, they have different treasury spot rate that you can apply to. Also, the market rate, right, change over time. You can think in certain way. If say you have a hedged stock option position, right? When you set it up, the risk-free rate is known and set in the contract. However, for bond, the price really depends on the market interest rate, and the interest rate change all the time. So that interest rate applied to the bonds should be changed over the calculation. So it's difficult. Okay. So using the binomial formula to price options on bonds can be difficult. It's much more involved. To summarize, pricing options with different underlying assets requires adjusting the risk-neutral probability for the borrowing cost or the leasing rate of the underlying asset. Thus, we can use formula for pricing an option on a stock with an appropriate substitution for the dividend yield. So here we want to see some similarity, right? For different underlying assets, the interest rate we can apply are all domestic risk-free rate. Even for the coupon bonds, we just know that all the rates are different, right? The dividend yield in the stock index can be replaced, right? For the currency, it's the foreign risk-free rate. For futures contract, it's still domestic risk-free rate. If we go back, right, it's gone. It's R minus R times square root of H, right? That's gone. And for commodities, it's the commodity leasing rate. Okay, if you can lease and short sell this commodity. For the coupon bonds, it will be the yield on the bond. Okay, that's the only kind of similarity between bond and stock in terms of option pricing. All right, that's the end of chapter 10.